So in this example, we're going to find the eigenvalues of a 2 by 2 matrix to get the section kind of started out. I realize there's a glare here on the board, and that's not ideal. The overhead light in my office isn't working right now, so I have to have the shades up on the window. So sorry about that. Okay, so first of all, finding eigenvalues in this section. Remember, an eigenvalue of a matrix is this number we usually use lambda to denote the eigenvalue. And it's a number where we have a non-zero vector x such that the matrix A times x is equal to the scalar multiple lambda times x. So eigenvectors are non-zero vectors x, where when you multiply a matrix A times x, what you get, it doesn't change direction at all. It just changes length. So it's just a scalar multiple. And so again, this is for a non-zero vector x. That's important for the logic that I want to run through real quick. So when we're finding eigenvalues, we're trying to find numbers where this equation can be satisfied by some non-zero vector x. If you move the terms to one side, and I'm going to skip some of the steps here since it's all explained in the notes, but if you move, let's say, we subtract lambda x from both sides, and then say I write x as I times x, and then factor out x. And this should be the zero vector here. Then we can manipulate this equation so that it now looks like this. A minus lambda I times x equals 0. So here we've got a homogeneous equation. And if lambda is an eigenvalue, then we have a non-zero vector x, because eigenvectors have to be non-zero. A non-zero vector x such that A minus lambda I times x equals 0. So in other words, the homogeneous equation has to have a non-trivial solution. Oh, and I'm using the bad blue marker again. I need to throw this one away. But what I'm writing here is non-trivial solution. We have to have a non-trivial solution to that equation, which would imply then that this A minus lambda I matrix, when we reduce, we do not get a pivot in every column. Or maybe another way of thinking about that then is this matrix A minus lambda I is not invertible, since it's not going to have a pivot in every column. And if it's not invertible, well, that happens if and only if the determinant of A minus lambda I is 0. And so this right here, this is how we're going to find eigenvalues, through this equation, which we refer to as the characteristic equation for matrix A. All right, so I'm going to actually do that over here. So first of all, I want to form this A minus lambda I matrix. So here's A minus lambda I. A is this matrix, 3, negative 1, 2, 0, minus lambda times the 2 by 2 identity matrix. So that's going to be this matrix, 3, 2, negative 1, 0, minus, if you multiply everything in here times lambda, you'll get a lambda here and a lambda here, and then lambda times 0 in these two spots, so those are still 0. And so if you subtract the corresponding entries, you have 3 minus lambda, 2 minus 0, negative 1 minus 0, and 0 minus lambda. And what's going to happen every single time is you end up just subtracting lambda along the diagonal, and then everything else stays the same. So I'm going to come back to this side now. So if we find, the plan is to find eigenvalues by solving this equation for lambda. Now we have the A minus lambda I matrix is this guy right here. So we want the determinant of that. So I'm going to denote that with these vertical bars, like absolute value bars. All right, and so to find the determinant, we do this sort of cross-multiplying thing for a 2 by 2. we do 3 minus lambda times negative lambda minus 2 times negative 1. So if I distribute the negative lambda here, well, I'm going to multiply these guys first. So negative lambda times negative lambda, that'd be positive lambda squared, which is why I wanted to multiply those first. And then negative lambda times 3, so that's minus 3 lambda, and then plus 2 here. And so this right here is what's referred to as the characteristic polynomial for the matrix. When you take this characteristic equation, determinant of a minus lambda I equals 0, that's going to turn into a polynomial every time. And we call this, like I said, the characteristic polynomial. So we want to find the zeros of that polynomial. Maybe we'll be able to factor it. If not, you can fall back on quadratic formula if it's degree 2 like this. But in this case, I want two numbers whose product is positive 2. So they multiply to give us positive 2. And the sum is negative 3. They add up to negative 3. So negative 2, negative 1 would work. And it doesn't hurt to double check, especially it's probably been a while since you had to factor anything at this point. So if I think through multiplying this out, I would have lambda squared, okay, that checks out, minus 1 lambda minus 2 lambda would give me minus 3 lambda, and then plus 2. So that looks good. And now you just set each factor equal to 0 and solve for lambda. So we get lambda equals 2 or lambda equals 1. And these are our eigenvalues.